So in the last two videos, we did the linear tuning method and the non-linear tuning method for boundary value problems. But this all leads us to, well, why bother making these initial value problems? Why not just attack the boundary value problem directly? So here, it's the introduction of finite difference method. Now, the finite difference method is a whole school of methods that can be used for partial differential equations, ordinary differential equations, and actually it is a precursor to finite element as well. It's a very simple extension of what we've seen with the Euler method. So first, as always, let's just do the generic. We are interested in a boundary value problem. We have a second derivative equals some function of x, y, and y dash. We have our boundary conditions at A and boundary condition at B. So we have a left and right boundary condition. We discretize the differential equation into a difference equation using a difference operators. So we have to deal with different parts. If we want to discretize the first derivative, we have three options. We have a forward differencing method. So I always think about these methods is, instead of thinking about x, think about time. Forwarding differencing method is actually thinking about using the future as a present almost. It's kind of counterintuitive. The backward differencing method, using the past to predict the future, and the center differencing method, which is a variation of our leapfrog scheme. And so what's interesting about that scheme is it is second ordered. It's more accurate, but it has some issues. It can result in an unstable solution if used incorrectly. But it's a fine method. Now, that approximates the first derivatives. For the second derivatives, the most classical one used is the central differencing method. We would have seen this when we did the Adams-Bashford and Adams-Moulton methods. The top line there is actually how you approximate the second derivative using them. So this is a collection of two notebooks. The first notebook will do the simplest type of equation just to illustrate what happens, and the second notebook will extend this ever so slightly. So we're just going to approximate the second derivative dy dx d2y dx squared is equal to 4y. So it's a very simple one, and our left boundary condition and our right boundary condition. So as always, we discretize the domain. That's always with the finite difference methods. That's the first thing you should always do. Discretize the domain, find out what you're looking for, and that'll help you approximate the answers. So, actually, just to note that the first and last point in our grid is known. And I should have been doing this with the other ones as well. Green is known. So you have your different distinction of color coding. So what happens to our equation? Our second derivative gets replaced by the center difference method. So 1 over h squared d2y dx squared gets replaced by 1 over h squared yi minus 1 minus 2yi plus yi plus 1. It might seem weird that I write in this opposite order, but the reason why it's order will become apparent when we set up the matrix. And that's true for I is equal to 1 to n minus 1. Why isn't it for I is equal to 0 to n? Because if we went that far, we'd have a y minus 1 term and we'd have a y11 terms, neither of which we know. So what you get here is 9 equations in our scenario. For I is equal to 1, we have our h is 0.1, so that's 1 over 0.1 squared, y0. Now it's in green and y10 is in green because there are known conditions, there are boundary conditions. Everything else here is unknown. So what we have here is that's 100 times y0, minus 204 times y1, and 100 times y2. And all these equations look the same, but note, the first equation has y0, y1, y2, second equation y1, y2, y3, and so forth. Yeah. So if we rearrange our equation by bringing everything we know to the right hand side, just a small change is the top equation and the bottom equation are different. And this can now be written in a very simple matrix form. Yeah. The diagonal of our matrix is minus 204. The off diagonals are 100 because the diagonal is that term all the way down, and the off diagonals are the one to left and right. So to set up the matrix, I set up a matrix that's 9 by 9, and I just set all the diagonals to be 204, and the off diagonals to be 100. Yeah. And here is the graphical representation of it. You see strong negative, and off diagonals are just the same. Yeah. y1 to y9 is what we need to know. So what we have is ay is equal to b. B in this case is very straightforward. B is just the vector that has 100 times the right boundary minus 100 times the left boundary. Yep. That's our right boundary, left boundary, right boundary, and we just multiply by 100 because that's exactly what we have here. Minus, minus. So now we have all zeros, and top and bottom, or left and right boundary, is taken care of. Oh, it should be noted here, because Python starts at 0, our vector goes to n minus 2. It's just a little thing to keep in mind. So to solve, all we do is the inverse, which is inverse A of NP linear algebra A. Here is our inverse matrix. See, it's a bit more complicated. There's a bit more involved in it. And we multiply that by our B. And that gives us our solution to the problem. Yeah. The first and last point are known, and that's a solution. And here's our exact. So it's very straightforward, and it's very adaptable. So let's see another example of it. So here we have a slightly, not much more involved equation, but we have 2x times dy dx. Y0 is equal to 1, y1 is equal to 2. Once again, our discrete period. Using the same difference equations, this gives us our difference equation. This is our differential equation. Our difference equation is this. Differential equation. The difference equation. Yes. So, now, do note here, we could do a couple of different things. Here I use the centering method. It's fine. And just need to fix that. That should be plus 1, minus 1. Yep. So 2xi times that. And so now I rearrange this because I like to rearrange it. This will be rearranged in a second. What I do is I gather together the yi minus 1 terms and the yi plus 1 terms and the yi terms. So that gives us 1 over h squared for the minus 2xi divided by 2h. Yeah, that's our term here. Our diagonal is actually quite straightforward. It's minus 2 divided by h squared plus 1. The reason why I have the minus there is because I brought the minus on the outside. And lastly, the yi plus 1 term is 1 over h squared. So like in the previous case, we have 9 equations, 9 unknowns, y1 to y9. Rearranging the equations, what we do is we bring across anything that has as known to the right hand side. So once again, that's equation 1 and equation 9. We bring that over. Now, the difference here is the matrix of diagonals are a function of x, so it'll change at every single point. Now, the representation of that, the way we write it is very straightforward. we include an I plus 1 here times h, because that's our definition of xi. And so therefore we see an increase and decrease. Now it's very subtle here because the dominant term is the h squared, but still in there. Yeah? Like before, we have our y plus 1, and now our b vector is something more interesting. We have our boundary, and we have the f component, which is 3x squared. Yeah. So here minus 2xi. So we have this minus 200 term here. And once again, we get our matrix, we invert our matrix, and we get our solution, which is a sigmoidal looking solution. So that covers the basic of finite difference methods. It also covers the basics of boundary value problem methods. So